Today we're going to do section 1.6, but before I start, let's scan the textbook. Okay, this is the page that's already been scanned earlier, and so I'll show it to you quickly again. Next, page 28 and 29. Okay, a little closer. All right, and then the top part and the bottom part. All right. Next, page 30 and 31. Okay, okay, here's the entire page, and then the top part and the bottom part. Let's pull back a little bit. All right. And the last two pages, let's see, first the whole screen, okay, and then the top part, okay, and the bottom part. All right, and that should be it. And oh, I better not forget the answer section. Okay, today is we have a new answer section page, which is right here. Let's see a little closer. Okay, and then the top part and the bottom part. Although we won't be needing the bottom part today, but this is just in case I forget to do it next time. All right, so that's that. Now, before we start this section, I want to quickly remind you Cramer's rule. Okay, Cramer's rule is how we solve simultaneous equations. And in this case, this is a 2x2 Cramer's rule I got out of Calculus 3. But you can find Cramer's rule anywhere, really, nowadays. Just find it online. Now, you notice that the Cramer's rule, here's how you solve for the variables, okay, given that this is conditionally true. And also I want to mention a couple of the properties of the determinant. First, if you take a constant that's being multiplied across a row or column of a determinant, you can just pull the constant out and the determinant value are the same. Secondly, if the determinant is transposed, in other words, see, we have A1, A2, A3 going across in this determinant, and this one goes down, and B1, B and C the same way, then the determinant is the same. That is, you can write it down or write it across, the determinant of the matrix will end up being the same. Now, if you don't remember how to calculate determinants, it's a straightforward but somewhat detailed process. So please look that up yourself, as I don't want to review determinants here. It's taught in algebra, I believe. So having said that, let's start our section. So let's start on page 27. Now, page 27, first we talk about Cramer's rule and specifically how to calculate the determinant. Your book even gives it a name. I don't remember. It's called the Laplace's method. It's just how you calculate it. Okay, so please look that up if you don't remember. It's the first term, and then you cross multiply minus the second term, then cross multiply, etc. Anyway, so let's look at theorem 8. Now, theorem 8, we have a bunch of stuff, okay? They all belong to C1, which means they have continuous first partial derivatives. And then the big F and big G, once you plug in the small f and small g, will be equal to 0 all the time. Okay, that's what the three equal lines are for. So they are identically 0. And then the determinant, the triangle there, which is F1, F2, and G1, G2 is not equal to 0. If that is the case, then we can calculate F1, F2, G1, and G2 by those four complicated looking formulas. Now, we're probably not going to go by this. We're just going to each time derive this thing ourselves, just so that we can be clear. Now, to see how this is done, let's look at the next page. We're on now page 28 to see the proof of theorem 8. And the proof of it is that we're going to differentiate those equations that we just saw. That is the big F. Okay, let's take the derivative of big F right here. This is, where's big F? Right here, right. See, big F is all this stuff, right? Well, they're going to take the partial derivative of big F with respect to x. And similarly, we'll do the same thing with small f. Now, if you do that and do it very, very carefully, all right, so you will end up with, based on what we know about partial derivatives, that will be a big F1, F1, and big F2, small g2, and so on. So we will arrive at these two equations. Now please sit down and do this like a homework, and yeah, derive this yourself. That is really the only way to get a hang of this. Otherwise, it all looks like a confusing mess to you. But once you take the derivative, you realize that it comes out nicely. And then once it comes out nicely, what you're going to do is this. See, I did it. Please do what I did, right? If you have F1, you come up with this first equation, okay, and then come up with a second equation. And then what you do is, right now, your F1, what are we doing here? We have F2, G2, and then, yeah, you have F2 and G2 right here for some reason. Right, that's because I was doing, no, this is partial y, excuse me. I think your book first, the first one your book did is partial with respect to x, so which you end up with F1. And then you solve this equation. So to solve for the first part of the equation in the theorem, where we need to figure out what F1 and F2 is, right? And what we're going to do is use the Cramer's rule that we just did from this particular equation, okay? And so, or you can just stare at this until it makes sense to you by double checking. And so we solve this equation. Notice this equation has F1G1 and F1G1 in both equations, which means we can solve them like two simultaneous equations with two unknowns, and by Cramer's rule, and that's where this thing will come out. I mean, that's where we have the solution. Now that is so F1 and G1. F1, I think it was F2, right? Was it F1 G1 or F1 G? F1 G1, sorry. So F1 and G1 is calculated by taking partials with respect to x. Now similarly, F2 G2 can be done by taking partial derivatives with respect to y, which is what I did here. Okay, now let me show you. So by taking the partial with respect to y, I come up with a very similar set two equations. Please do this yourself. And then by Cramer's rule, I was able to solve F2 and G2, which is just what the Theorem 8 says. So please do this yourself, to convince yourself of how this is done. Now remember how to take the big F. The big F assumes that everything is an independent variable. So to take the partial derivatives of the big F, then we have, so big F with respect to the first variable, that is the same as F1 then is big F with respect to U, right? And then F2 is big F with respect to V. Now in this case, we have to apply the chain rule because U got replaced with Fxy. So, but the big F1 itself, however, is just partial with respect to U, and you don't have to worry about anything else with it. But anyway, and what I'm saying is more confusing than it is difficult, and the only way to solve it is really just to do it yourself. All right, so with that, let's look at the next thing. Okay, the next thing is called the Jacobian. The Jacobian was mentioned briefly in Calculus 3, and that was about it. So, but what it is the definition of some of the partial derivatives in some kind of a matrix form. The reason is because this shows up a lot, okay? I mean, for example, like look at how we calculate F1, right? There's a matrix up there, and the little triangle is a matrix down there. So we're gonna, and all these are matrices of partial derivatives of something. So to write it easily, we are going to redefine the matrix to make the writing a little simpler sometimes. And then, so we're going to adopt a notation. That is, the matrix of the Jacobian is defined like this. We'll write down FGH on top, and then the independent variables UWC on the bottom. And what does that mean? That means we will write down F1, G1, H1, in line of FGH, and then the variables, which is UWZ in this case, will be accordingly. Now, when you look at this more carefully, why is the second row, it says F3, G3, H3? Why is that? The reason is because the variables, the F has a whole bunch of variables, okay? The FGH has variables U, V, W, X, Y, Z. So to do this determinant, U is the first variable. So the first row is F1, G1, H1. The second row is W, right? W is the third variable. That's why the second row is F3, G3, H3. And lastly, the Z is the sixth variable. That's why the last row is F6, G6, H6. That is, you can take the partials with whichever of the three variables out of 6 that you need the Jacobian for. So there are various Jacobians, and depending on how things are done. Now, you might notice that so far we have the determinants are written like this. Okay, look at the previous page, theorem 8, where it determines F is on top, right, and then G is on the bottom, but the Jacobian is written differently. We have F. See, the Jacobian is written as where is it? Here. Now, Jacobian is F is on one side, right, the first side, and then G is in the middle. I'm talking about this thing. G is in the middle, and then H is in the last row. And why isn't it? Is actually this is the same as that. Now, why isn't it written like that? Because that's what we've been doing. The reason it's not written like that is because this way it lines up with the FGH better. See, you have FGH here and then FGH here. But they are the same thing because the determinant, as I mentioned a little earlier, is the determinant. You can transpose it, which means swapping the rows and columns, and doesn't change the determinant. So you can write it either way, and it is fine. All right. So that is how the Jacobian works. Now, to show and to give even a strong further example, so to pound the concept home, let me move this. Okay, it's focused in. Where's my hand? And wrong side. Okay, it's on this side. Okay, now so let's see. Now, bearing in mind that the variables are in line U, V, W, X, Y, Z. So let's say we need to do partial GFKH with respect to Jacobian of WXZU. Now, how would you do that? Now, we will do this exactly like it says. Okay, so first we'll write that. Going across, we'll write it as GFKH, okay? So it's GFKH all the way across. Each row is the same. Now, what's W? The first one is W. W is the third variable. So the third row is G3, F3, etc. The second row is X. What's X? X is the fourth variable. So the second row is G4, F4, K4, etc. The third, and the same principle applies. The Z is the sixth variable. So the third row is G6, F6, etc. And finally, the last variable is U. What's U? U is the first variable. So the last row is G1, F1, K1, and so on. Okay. So that is. So please work this out yourself to see how that makes sense. And but anyway, that's the Jacobian, and the Jacobian is to represent these matrices. Okay, each of these things are Jacobian, basically, and you can write them exactly in the Jacobian form. So as you can see, the Jacobian has various functions on top, and then various independent variables on the bottom. At least that's what they are taking derivative with respect of. Okay. So eventually then F1 is, which is this thing, okay, F1, as you can see then, F1, which is this thing in theorem 8, okay, we can write it as a Jacobian, except that this thing, we have to swap this, okay, so that F, it goes across as FG, that way in the Jacobian tradition. So we have, you can confirm that this relationship is the same as the equation written in theorem 8. Okay, yeah. So please confirm that yourself. And then next we have let's see. Now I will look at this. Now notice this Jacobian thing happens to have a mnemonic device that's built in. That is, let's say you want to do partial U, partial X. Now, look at the Jacobian. Now, if you pretend that these symbols are all variables or something, then when you do the division, every symbol, most symbols get canceled out, okay, except for x and u. So when you do the division, it ends up being partial u over partial x. Okay, if you look at this thing. And in general, when you do this Jacobian, you will put the x where, see, down here is partial u, partial v, and then you replace x where u was over here. That is, see, u is in the first position, what they're taking derivative with respect to x. So you will put x in the first position, and then this formula will pan out. Now, that's what this is saying, is that we can use it as a mnemonic device to help remembering the formula. But that's not that critical right now. Please look at that yourself. And if you don't remember this now, you will after you've done enough of it. And then you realize, oh yeah, we can just remember it this way. So that's that. Now, so next, let's look at the following page, page 29. So in section 29, 6.3 on page 29, let's look at an example where we have more variables, 4 variables. Now, just because they have more variables doesn't mean our story change, okay? The du by dx, when all is said and done, is still equal to the division of the Jacobian as it shows. Now, when there are more variables, you need to keep very careful about who is the dependent variable and who are the independent variables. Now, the dependent variables are the ones that the ones go on top, okay? And then eventually in the Jacobian, however, that's what you're going to be dividing by. For example, let's say UVW is the dependent variable, then your formula will have UVW on the bottom. Right here, see, in the denominator. And then the du by dx, the partial x will replace the u position in the formula. That is, see, we're doing du by dx, so we're going to do uvw, those are the dependent variables. And then x will replace u, which happens to be in the first position, okay? So, and when you do this, then that formula will work out to be du by dx. Now, you say, well, that doesn't look obvious to me. That's because you haven't worked it out yet. So please work this thing out. Like I see, and here's what I did. And I took the partial derivative with respect to x of all 3 equations, and I came up with this thing. Please do this very carefully yourself. And remember, for the big F, each variable is independent, right? And then it is, but when you take partial with respect to x, then you will have each one that got substituted will have du by dx in it, and dv by dx, etc. So you come up with these 3 equations, and then you apply Cramer's rule for 3 by 3 things, which is the same thing. And then then you notice it equals to this, and you can pull the negative sign out. As we mentioned, that you can pull out the constant that's in the entire row. Pull the constant out of the determinant, and so I'll pull the negative sign out, which equals to this. And that, please confirm that this thing is exactly this thing, because in this case I'm still writing it the old-fashioned way, okay? Whereas the Jacobian wants you to write it across, but there's no difference, okay? And so please work this out yourself to make sure that this makes sense, and then all this will come out nicely. And it's easier to just, well, do it rather than hear somebody explain this to you, because everything is straightforward, but it is tedious and there are a lot of variables, and you have to focus and keep everything straight. All right, so next, let's consider the case where we have 4 equations, 4 big functions, such as the functions, okay? It says that we consider these 4 functions, okay? Let's say they're all equal to 0. So that we can calculate, say, partial x, partial z. Okay, so now it's just like the top case, right? Except that now we have 4 functions instead of 4 functions. That means 4 simultaneous equations. So our Jacobian will look like this. And again, please confirm this claim yourself. Okay, I have done it right here. Well, most of it. You see, I have 4 variables, and keep very careful track of all the variables, who's independent and who's dependent. Well, we have these 4 things will be dependent, okay, which means the only thing that's left independent is y and z. So we can calculate things such as uy, vz, wy, xz, and all kinds of stuff, right? So, but to calculate any one of these, so let's say we take the partial with respect to z. Then you're going to write down 4 equations that look very similar, okay? Instead of, that's the first line. The second line looks just like the first line, except that you replace the word f with g, and so on. So then you will end up with the division of the, what is that? The determinants, right? Which can be written like this, okay? If you, by the time you're done. What happens is, being that we're doing partial x over by partial z, so we are going to use the, right. So then these are the dependent variables, okay? And the independent variable, which is z, we'll write it down in x's position, replace it. So these two look the same, except that z is replacing x, and that would be your answer. And where's my negative sign? I think I forgot the